Hello everyone, my name is Fanchen Bao. My presentation today is titled Comparison of Fingerprinting Performance in RSSI-based Localization with Assistance from Gaussian Process. Before we dive into the Gaussian process part, let's first get familiarized with RSSI-based Localization. RSSI stands for Received Signal Strength Indicator. It is a type of measurement of radio frequency signal strength that a receiver can acquire from a sender. Given that as radio frequency signals travels through the air, its signal strength decreases, there is a negative and non-linear relationship between RSSI and distance. In other words, we can think of RSSI as a feature that contains information regarding the position of the sender relative to the receiver. If we want to leverage RSSI to perform localization on mobile device, we need to have the mobile device send some sort of radio frequency signal. And luckily, this is exactly what's happening all the time if a mobile device has its Wi-Fi on. When the Wi-Fi is on, the mobile device constantly sends something called Wi-Fi probe request. It sends this Wi-Fi probe request in order to make connection with an access point. And it's fairly easy to capture these probe requests on a sensor, and we can read the RSSI measurement from each probe request on the sensor. Now imagine we have 4 sensors on the corner of a rectangle and a mobile device inside the rectangle. Whenever the mobile device sends probe request, it can be captured by all 4 sensors. And since RSSI is correlated with distance, the RSSI measurement of each sensor is dependent on the relative location of the device to the sensor. And when taking into consideration all the RSSI measurements, it provides us a possibility to localize the device. And this is the basics of RSSI-based localization. One of the easiest methods to perform RSSI-based localization is called traditional fingerprinting. I'm going to explain how it works. Imagine in the rectangle surrounded by the sensors, there is a grid. And each point on the grid is called a reference point. The traditional fingerprint requires an offline phase where we collect RSSI measurements at each and every reference point. For example, we are at reference point 1 or RP1, and the RSSI measurements from the 4 sensors are -20, -50, -40, and -60. We will record this data in a row in something called a radial map. In other words, what we're doing is to use a vector of RSSI measurements to represent a reference point. Or we can say that a reference point is fingerprinted by the RSSI pattern in each row of the radial map. In the current case, we can say that RP1 is fingerprinted by RSSI vector -20, -50, -40, and -30. We can repeat the same process for all the other reference points in the grid, and eventually we will acquire a radial map with RSSI fingerprints for all reference points. After the radial map is constructed, we enter the online phase where we perform localization on an unknown device. As the unknown device sends out probe request, the sensors can pick up its RSSI measurements. Thus, the location of the unknown device can be represented by an RSSI vector. And in our case here, we can say the unknown device, the location is characterized by RSSI vector -45, -40, -55, and -50. And now, our job is to look through the radial map and find the reference point whose RSSI fingerprint that mostly resembles the RSSI vector obtained from the unknown device. Then, we can say this reference point is the predicted location of the unknown device. The computation of this resemblance can be as simple as the Euclidean distance between the RSSI fingerprint here and the unknown device's RSSI vector. And we have computed the Euclidean distance for all these 3 reference points, and we can see that RP2 has the smallest Euclidean distance. Therefore, in our case, we can say that RP2 is most likely the location where the unknown device has originated. Now that we have covered the basics of RSSI-based localization using traditional fingerprinting, let's take a look at where Gaussian process can play a role. Gaussian process is able to model arbitrary complex relations, such as the one between RSSI and location, as long as we provide sufficient prior observations. A physically collected radial map is a good source of such prior observation, and we can use the radial map to tune the hyperparameters of a Gaussian model, specifically the kernel function. Once a Gaussian process model is trained, we can generate an artificial radial map at any dimension and any resolution because Gaussian process is continuous. In our implementation, the input of a Gaussian process is the x and y coordinates. The output is the RSSI measurement. We use the arithmetic mean of the output value as the mean function and a squared exponential plus noise kernel as the kernel function. After we have trained the Gaussian process model using the physically collected radial map, we are able to construct a new radial map completely based on Gaussian process. Here, we show one application of Gaussian process, which is called GP-based fingerprinting. In this method, the new radial map generated contains 4 Gaussian distributions for each reference point. We can see that not only can we generate radial map for reference points that have been physically collected, such as RP1, RP2, and RP3, we are also able to create radial map on reference points that have never been physically visited, such as RP4, RP5, and RP6. And this is the power of Gaussian process. We can achieve this because Gaussian process has learned the shape of the relationship between RSSI and localization. And therefore, based on the shape, we're able to predict RSSI at any location. And of course, for the GP-based fingerprinting, we're not actually using the RSSI value, but the Gaussian distribution of RSSI value for each element in the radial map. During the online localization phase, we perform a similar process as the traditional fingerprinting in that we compare the unknown RSSI vector to each and every reference point. However, instead of using the Euclidean distance, we compute the likelihood of the unknown RSSI vector belonging to each reference point. Now, this is possible because the radial map consists of Gaussian distribution instead of just values. Now, for instance, let's say we want to find the likelihood of the unknown RSSI vector belonging to RP1. We will first compute the PDF of -45 belonging to the Gaussian distribution defined by mu11 and sigma11. And then we compute the PDF of -40 belonging to the Gaussian distribution defined by mu12 and sigma12, so on and so forth until we obtain 4 PDFs from each RSSI measurement in the unknown RSSI vector. Now we multiply these PDFs together, assuming that each RSSI measurement in the RSSI vector is independent, and then we will acquire the overall likelihood that this RSSI vector belonging to RP1. And we perform this likelihood computation for all the reference points, and we pick the reference point that has the highest likelihood. And we say that reference point is most likely the localization result of the unknown device. Another way to incorporate Gaussian process is to use a GP-assisted fingerprinting. Now, like the GP-based fingerprinting we just discussed, we perform the same training on Gaussian process model, But the new radial map is not composed of Gaussian distributions. Instead, it consists of RSSI value, and each RSSI value is the mean value of the corresponding Gaussian distributions. In other words, the radial map from GP-assisted fingerprinting is of the same type as the physically collected radial map, except all RSSI values are artificially generated through Gaussian process, and we're talking about a much expanded radial map however we want. Since the GP-assisted fingerprinting uses the same type of radial map as the traditional fingerprinting, we can use the same Euclidean distance method to find the RSSI fingerprint that mostly resemble the unknown RSSI vector. And we can use the same method as well to find the reference points that mostly likely to be the originator for the unknown device. Now that we have gone through the three fingerprinting methods, let's take a look at the evaluation of the localization performance. We are going to compare under two scenarios. One is full data, which means all the methods can see all the data available. And the other scenario is called 10% data. This means all the methods can only see 10% of the data available. So with the 10% data, what we're doing is we are reducing the availability of the data to simulate what most likely will happen in a real scenario. Within each scenario, we compare the localization performance of the traditional, GP-based, and GP-assisted fingerprinting. And also, we talk about the criteria for localization performance. It is provided by the CDF curve of localization error. Now, what is a localization error? A localization error is defined as the distance between the predicted and the actual location. And the CDF curve can be seen here. We are ignoring the data analysis for now, just looking at the CDF curve. So this is a CDF curve. So what a CDF curve can tell us is the probability that localization can achieve an error small or equal to a certain value. For instance, given this CDF curve, we say that the likelihood, the probability that it can achieve an error smaller or equal to 2 is about 40%. And apparently, the CDF curve on the top has better performance than the ones at the bottom. Now let's take a look at the actual analysis. The blue lines represent the full data scenario, and the red lines represent the 10% data scenario. And we can see that all three methods under the full data scenario have similar performance because their CDF curves are very close to each other. We can also see that the traditional and the GP-based fingerprinting under 10% scenario, we're talking about the red circle and a red triangle, they also have similar performance since their curves are close together. But their performance is much worse than the full data scenario. So these curves are performing worse than these blue curves. What's interesting is the red cross line. Now the red cross line is this line. So the red cross line represents the GP-assisted fingerprinting under 10% scenario. It has much better performance than the other two methods under the 10% scenario, and in fact, its performance is approaching that of the full data scenario. Therefore, we can say that the GP-assisted fingerprint's performance is very resilient to the drop in data availability. And because of this, the GP-assisted fingerprinting has the best chance to be successful in the real world where RSSI measurement is most likely sparse. Before finishing this presentation, I would like to point out the area for future research. First, the current implementation of GP is through a static arithmetic mean for the mean function. We'll explore how a dynamic mean function can be fit to the GP model. Second, the data used for the analysis was collected in an ideal environment with the least amount of noise. it'll be interesting to reevaluate the performance of the methods when noisy data is provided. Furthermore, we can also compare GP-related methods with other non-fingerprinting-based methods, such as trilateration, machine learning regression, and machine learning classification, and see whether the GP-assisted fingerprinting can still perform the best under sparse data. Thank you very much, and here are my references.